Hello there, welcome back to AP Examined. This is our 7th lesson on limits, and we'll be going over tangent lines in this lesson. Now, to begin with, I'd like to do a little review of something called the secant line. I'm just going to go ahead and type this in here. Now, the secant line is something you might remember from geometry. This is, let's see if I can do a circle here. Okay, the secant line is going to be any line that we can draw from one point on the circle to another point. Something that just cuts right along. And this actually extends infinitely in either direction. And we can draw secant lines anywhere like this. These are all secant lines. And then, if you remember, we actually have seen the tangent line before in geometry with the circle again. Now, the tangent line is going to look something like this. It touches at only one point on the circle, and extends infinitely in either direction. And we can see that the secant line and the tangent line are related because the secant line involves 2 points where the tangent line involves only 1 point. So, for example, if we took this line, secant line here, and we started from over here, and moved along the outside of the circle here like this, and kept going, and going, eventually we're approaching the tangent line for this circle. And starting from there, it would look something like this. Eventually we're going, eventually we've got a tangent line going straight through that point. As we move along here, once it hits this point, it's just a straight line going through there. Now it turns out that this is a very useful thing to understand in calculus, and that it's something we'll be using a lot. I'm not going to check this what is a tangent line box yet, because although we know what it is in a circle, we have to go and see what it looks like in a curve. So I'll clean this up, get rid of this. So we know what the secant line is. We can cross it out. Now, let's go ahead and draw ourselves a curve. Okay, that's good. Now, we'll go with the generic squiggly curve again. And let's say that if we take a line and draw it through this curve, boom, there's an example of a tangent line, because it's touching the curve at only 1 point. And then we could have another one like this, coming right up there against the curve at 1 point. But you might be saying, what do you do when you have something like this, where the curve is like a sine wave? Now, what is the tangent line at this center point? It doesn't exactly go straight through and touch only 1 point. It's actually going to look something like this. So our definition of a single point doesn't really work when dealing with squiggly curves. It'll work on something like this, where it's just touching at a single point there. But when we get to some of these rougher places, sometimes it can be hard to tell exactly where to put that tangent line. So what we're going to do is throw out our old definition, which says that it's just touching at a single point, and start fresh with finding the slope with calculus. Now, we can check this off. We know what the tangent line is, I guess. I'll give it the check. I said a moment ago that we wouldn't, but once we know how to find the slope with calculus, and we understand how to use calculus to find the tangent line, then we'll be fine. So how to do this finding the slope with calculus is using a limit. Now, I'm not going to show you what this limit is yet because I want you to understand it first, and then I'll just give you the definition. But let's go ahead and draw another curve here. Now, if you think back about what I showed you with the circle, you'll remember that I showed, here, let me just draw the curve first. Let's just do something simple like this. Alright, nice basic curve. Now, I first told you that you can use the secant line to find the tangent line if you make secant lines, multiple secant lines, getting smaller and smaller. If we draw a secant line on a curve like this, it would look something like that, connecting 2 points. And then if we make it smaller and smaller, as we move this second point here along this axis, we actually get something that's a lot like what we learned from geometry. This is how you find it with calculus, intuitively. You take this point here and move it along until you get one line. So these lines that we're making here, that are getting more and more like this, approach that tangent line there. Let's see, it looks something like that. These secant lines get closer and closer to this line. So all you have to do is make that secant line, which is just 2 points, and move that second point closer and closer until you reach that first point. Now, what we know from the algebra that we've done before is that if you want to find the slope of a line, let's see, if you want to know the slope of a line, something like this, a line has to have 2 points and a slope. Or, I mean, if you want to find the equation of a line, you need the slope, at least a slope and a point. But if you want to find the slope, you need 2 points, because you need a rise and a run. And you need some ratio of change as we move along the x-axis. So we can easily take this point here and this point here, or any points, compare any 2 points along here, and say how much did it go up versus how much did it go to the side. That'll be our slope. But over here we don't have 2 points, we only have 1 point. So how we do it is pretend we do have 2 points, we make a secant line, and then say what happens as the second point gets smaller and smaller, and eventually until that second point touches our first one, and what's the limit there. So you're probably seeing now how the limit is going to come into this. And I'll go ahead and erase this again and draw out our definition. So let's just go ahead and write this out. The slope m, I'll just write slope up here so you remember. The slope m equals the limit as h goes to 0 of f of x plus x naught plus h minus f of x naught over h. Now this looks complicated, but let's draw an example like we did before and see how this makes sense. Now let's do this. Make another graph. If we just draw a simple curve, actually I'll exaggerate it. I'll make it look like a parabola. So let's say we want to find the tangent line at this point right here. So what we do is we say we draw a secant line, pick a point up here. We'll start up there. So this is our x naught, right there. And then the second point out here, if we come down, this is x naught plus h. And this distance here is h. So that's what this actually means. Now what we're saying is, if you realize that what we're doing here, this is f of x, and this is f of x naught plus h. This up top, f of x naught plus h minus f of x naught, is the height, and h is our width. So if we have height over width, then you'll see that we're getting our slope. And this is more the rise over run. That's how I learned it. Our rise over our run. Now, this should start to make sense as we say that h goes to 0, because what we're saying is we take this point, we take h and make it smaller. We take it and make it go there, or make it go here. What happens is we make h smaller and smaller, like this, smaller and smaller, until h goes to 0. Until we get a tangent line to this function, something that looks like this. So this should make sense to you. This goes to 0, and we have our slope at a single point based on this rise over run function. Now, we know how to find the slope with calculus. That's what we have here. So make sure you understand this little limit here, and once you get what's going on with it, we'll be able to do some examples, and that's going to be what I'll be covering in the next video with some real examples, because we've had quite a few lessons on just concepts, which is really important, but now we can get back to the grind with some real problems from your textbook. So thanks for watching the video, and I'll see you tomorrow.